Hey, Clemens, come on up. Welcome, everybody. This is Panda, Panoramas, Displays, and Acquisition. This is the last talk session for SIGGRAPH 2012. I and the authors thank you for sticking it out this long, till the end. My name is Bob Koima. I'm a professor of computer science at Louisiana State University, and I'll be here keeping time. Our first speaker is Mark Colbert. That's right. Mark joined Google in 2010. He's a tech lead manager for Google Business Photos, which is part of Google Street View. His presentation is entitled Building Interior Multi-Panorama Experiences at Scale.
All right, thanks. Thank you all for making it out to the very last session at SIGGRAPH. Today I will be talking about building interior multi-panorama experiences at scale. This is work done by myself, along with Jean-Yves Bouguet, Jeff Bias, Spud Childs, Daniel Phillip, and Luke Vincent from Google, Jongwoo Lim at Hanyang University, and Scott Satkin currently at Carnegie Mellon University. So this project originated from Google Street View. And the idea in Google Street View is to capture the world's information using 360-degree panoramic imagery, or panos. This project's been around for the past 5 years, and we've driven and published millions of miles worth of data in over 48 different countries. What this has enabled is a very simple search and see paradigm. So for instance, if I was too lazy to go outside, I could simply search LA Convention Center and easily see what it looks like. Now, over the past couple years, we've actually been trying to expand the reach of Street View. And so what we did was we put our capture mechanisms on top of different vehicles, such as a tricycle. And we were able to go to places such as Stonehenge or, as we see here in this slide, the Kennedy Space Center. We've gone even further by putting our capture mechanism on top of trolleys. And we were able to go inside a variety of different museums around the world for the Google Art Project. But we want to go even further. And this brings us to Google Business Photos. So the idea behind Google Business Photos there should be some audio here. The idea behind Google Business Photos is to pretty much allow users to just use commodity equipment, upload to our servers, and then use our processing pipeline to be able to figure out how to build an ideal Street View experience from all this data. Once they've built the Street View experience using our toolchain, what they're able to do is publish it. And then so you can simply search for a restaurant like Gary Danko, and then you can just click See Inside, go inside that location, and just walk around that space. While the photographers are there, they actually also end up capturing a variety of point of interest photos to sort of show off more of the different variety of what's going on in that local location. So fueling this is our Trusted Photographer Network. This is a network of hundreds of photographers worldwide. This is a constantly growing ecosystem of these small, medium business relationships where photographers are going to business owners, trying to sell this package to them, and the business owners get their Street View experience of their location. But we need tools for processing the photographer's data, and that's where this talk comes into play. So today I'm going to be doing a more high-level overview on what we've been working on how to convert the raw imagery data that the photographers collect into panos through a process known as panostitching. Once we have the panos, I'll be talking about how we actually geolocate and orient all this data in the world, and then how we visualize the error, and we'll get more into that in a bit. So the basic idea is we start with this pano capture process. And since we're trying to scale it, we needed to be able to use commodity equipment. So we use normal tripods with normal off-the-shelf 360-degree pano heads and a DSLR. We also used fisheye lenses to reduce the number of photos that we actually collect. This becomes a bandwidth concern when you're starting to talk about that much data. But the problem is when you do perform panostitching with a naive approach, you end up getting a 30% failure rate. And most photographers don't like losing 30% of their data. So to go over why this doesn't work, let's go over how panostitching actually works. So the approach here is to first find sparse features. Sparse features are just image patches, as seen here, that relate to other image patches in other images. We're going to represent these by these green triangles. Once we have these sparse features collected for a set of images, as we see here with these two cameras, we can use these sparse features to then align the data with one another. We continue this alignment process for all the images in the pano. Now, once the data is aligned, we can simply project the raw data and use a blending algorithm to actually build our final panoramic image. Now, why is this hard? Well, what happens is if we look at the overlap region in the fisheye lenses, as highlighted in green here, it's actually in the highest distorted part of the image. So if I zoom in on this corner of this TV, the actual corner of the TV looks quite different in the two images. So what's going on here? So if we think about a fisheye lens as this sort of arc, we're sort of projecting this arc onto a flat plane, and that ends up giving us a large amount of distortion along the edges. Now what we can do here is actually take two planes that are 45 degrees apart from one another and sort of project the fisheye imagery data onto those planes. So this effectively kind of linearizes some of the components. So as we see here, this is two sets of images that actually had quite a bit of overlap, but if we linearly project it, we actually get even more overlap. And what this did was it improved our success rate from 70% to well over 95%, at scale. Now, once we have these panos, we need to figure out where they're located in the world. And this is essential to the Street View experience, because if you're in Street View and you click a link to go somewhere else, or you use what we call click to go to move around, if that pano's not in the correct location, that experience is broken. Existing Street View technology uses capture mechanisms such as GPS, lasers, inertial measuring units, and wheel encoders to do this. But due to our commoditization constraint, we only have images. So we need a 100% computer vision only solution. So this puts us into a class of algorithms known as structure from motion. And there's a large variety of different structure from motion techniques. The one that we've found to be working best for us at the current moment is based upon the photosynth approach presented by Snavely et al. In 2006. The way the algorithm works is that we first extract features, and then we find two panos with the most number of similar features. Once we've figured out the location of those two panos, we take the next pano that has the most number of features in common with the first two panos, and then inject that into our graph. And so we keep on building out the panos. Now, just as a visual example to understand what I'm talking about here, here's a small comic shop, and what we see with these first two panos is that we have a large number of correspondences. And what you see here on the right is the blue dots represent our estimated position of the panos, and the green and red dots actually represent the location of the features. So there was a large amount of overlap here, and we were able to figure out the positions of these two panos with respect to one another. Now what we do is we take another pano that has a lot of similar features, and we sort of inject that in there as well. And then we're able to figure out the pose with respect to this third pano, with the third pano with respect to the first two. And we continue this process until we've completely built out the cluster of all the panos that we're trying to link together with one another. Now this provides a really great basis, but if we look at the problem at scale, well, quite frequently we get this pano soup issue, where panos are just completely misoriented. Anecdotally, what we've been able to see why this happens is largely it comes from repeating patterns. So if you think of a carpet that has a very common pattern on it, that'll oftentimes mess up sort of these sparse features. Similarly, wallpaper messes it up, but also on walls, we have just blank walls and interior spaces quite frequently. So we're not able to actually find the correct locations of these panos. Lastly, these algorithms are designed for UGC photo type input. So typically when these algorithms run, you're running with about on the order of thousands of user-generated photos. What we're typically talking about here is on the order of tens of photos. So in order to understand why this doesn't work, we wanted to be able to visualize the error in some interesting way to actually figure out what's going on. But to understand how to visualize, we need to actually first compute the pose. To understand how we compute the pose, normal pose constraints are pretty much computed by having 6 degrees of freedom, where the position between the two cameras is determined by the 3D position and the 3D rotation. This ends up requiring about 5 degrees of, or 5 pair correspondences to solve for the 6 degrees of freedom. Now, we made a planar constraint because this is not only the way that the Street View interface works, but we also assume that the photographer is using a tripod that's at the same level the entire time. This allows us to actually increase our robustness because we only need 2 pairs of correspondences to solve for the 3 degrees of freedom. Now, once we have a pose estimate, we need to actually figure out which is the best pose estimate. And so we use a method known as RANSAC, or Random Sample Consensus. The idea behind RANSAC is that we first extract our features from our panos, and then we pick 2 pairs of features that are similar to one another. We use those 2 pairs to solve for our pose estimate. And then, once we have our pose estimate, we actually find the number of similar matches by looking at the other pairs of features. This is sort of the score of this pose estimate. We continue this process by picking another 2 random pairs, finding the pose estimate, and finding the number of matches. And then again. And we repeat this process thousands of times until we actually find the one pano that has the highest number of matches. And the one that has the high is known as our ideal pose estimate. Now, the problem with matches is that they're great for this voting problem, but they're not very good for actually determining the overall quality of the estimate, because they actually end up representing more of how many features we had to begin with instead of the actual quality of those features. So we came up with something different called random sample statistics, or RandStat. The idea behind RandStat is that we first, once again, extract the features and pick two random pairs of features, and then we create the pose estimate. But here's where it changes. So the most important thing in the Street View experience is what's known as the direction of motion. The direction of motion is effectively the way you travel when you're going from one pano to the other. For those familiar with computer vision, it's the epipole. So what we did was we took the direction of motion and sort of discretized it into these bins. And so each pose estimate that we create actually just sort of provides a vote for each bin. As we see here, this one voted for the 90-degree bin. We pick another two random pairs, produce a pose estimate, and let it put another vote into a bin. And we continue this process thousands of times until we end up with a nice histogram. So outside of this nice example, if we look at one with 1,000 or with quite a bit higher degree of fidelity in our histogram, and thousands of samples run, what we end up getting is this very nice Gaussian shape. And this is actually something that we've seen with thousands of manual inspections of pano pairs. What's interesting about this Gaussian is that first, the peak of the Gaussian actually represents the RandSat optimal direction. What we also get, though, in addition to that, is the direction of motion uncertainty as seen by the standard deviation of the Gaussian. We also have this uniform noise level that actually just tells us how valid is this actual estimate that we're generating here. So to help illustrate this, let's look at a couple different pano pairs. So in pair A, we have a couple of very unrelated panos. In fact, one pano's outside and the other pano's on the inside. So the only thing that's actually matching between the two of them is the stuff that's seen through the windows and the door. As we can see here, there's actually quite a wide standard deviation and quite a bit of noise. But in pair B, we have two panos that were taken from the inside, so there's actually they're very similar. And what we end up seeing is very low noise and very sharp peak on our actual estimate. Now with this Gaussian approach, it actually represented a very lightweight way of communicating how well or how good the pose was. And what we've been working on in parallel, knowing that the pose generation was actually not producing good results, was a way for editing Street View pose directly. So what I'm really excited to do right now is try and risk it and do a demo for all of you. And this is the first time that anyone's seen our pose estimation tool outside of Google and our Trusted Photographer Network. So this is our tool. As you can see here, we sort of provide a simulated Street View experience. And the user can very simply just walk around the different location. What they can also do is they can actually see the underlying panograph on the left. So this is what was generated by our pose estimation algorithm. What they can do in this space is they can actually just simply translate, rotate, and scale the overall estimate with respect to the world by using either satellite data or matching it to existing Street View data. Now, what we were able to do here was we were able to actually visualize what the pose estimate actually, or that RandStat data that I just showed you before, as frustums. So you can see here, it might be a little bit hard to see on the screen, but what you can see are these little frustums that actually represent that likelihood of these two panos being in the correct location with respect to one another. Now, what was interesting to us was we just thought this was a nice little development tool, and we turned it off eventually because it was just for us. But we got very quick feedback from all the photographers asking for this feature because that was allowing them to help position the panos. So in other words, when the photographers were trying to locate a pano and move it around, this was really helping them position the panos with respect to one another by having all this sort of visual data that they could have access to. But we thought, wait, can't we do more with this? So what we realized was that this is actually quite a low-dimensional problem here. We've taken a very complex, typically very high data-intense vision approach, and we now have a lot of really simple data. And what this can actually do is start guiding the user and allowing them to sort of figure out how to do edits, or allowing them to do sort of rough edits, but then actually just go in and allow the computer vision to actually correctly fix it. So just to sort of show that again, this is really cool. You can actually use the vision that's already computed and just simply correct your pose on the fly in the client without having to go back to the server or do anything crazy like that. So in summary, what we've shown is a novel approach for stitching connected pano sets at scale. We provided a vision assist pipeline for photographers to build Street View experiences, and this has expanded to a large numbers of businesses per day. Now, what I'd like to also show you is something that's never been seen before outside of Google, which is our Pulse. And what our Pulse allows us to do is to sort of visualize all the different panos that have been or all the different businesses that have been recently published. Now, here's a really neat business in Japan. But one thing I want to show you here in the lower right is if I start zooming out, you start getting an idea for how many businesses around the world that we're collecting and publishing every day. And this is just a subsample. So with that, I'd like to thank all of you for coming, and I'd like to open it up for questions.
That's fantastic. If you've got questions, please come to the mics. Now, where are our mics? There and there. Okay. Well, since we have a few moments, in my experience with panorama stitching, the most problematic case is often the generation of the matching points in the first place, the little green triangles. Yeah. How is it that you ensure that these are actually good? What I would find is often they wouldn't be distributed evenly across the image, or they wouldn't be in places that were useful. What are the details there?
So that's a great question. So, I mean, they were actually in all the wrong places, to be honest. I mean, they were never in the areas where we needed it to be, which was the overlap region. So the linearization was the first try at that problem. Overall, outside of that, what we did was we used a variety of different types of features. We currently use something known as Congas, which is a Google internal proprietary feature type. Standard sort of Gabor wavelet, histogram gradient type approach. And we've tried it out just on a large variety to see what works best. But you're absolutely right. That's a very big problem, and that's where the 5% problem comes in. What we do is that we actually learn from our existing data sets. So we have so many panos coming in from cameras, we're actually able to learn a global intrinsic value for each of our camera types that photographers are using. And so if we can ever get the actual answer to be completely correct because of the lack of features, we use that prior knowledge that we've learned by just having a massive number of panos created to actually then stitch it in a way that's very close to correct.
Okay, so the answer is Google magic. Any more questions?
Sure. Now that you have all these panoramas, are you also looking into dense 3D reconstruction, like doing stereo on pairs of panorama?
I mean, yeah, that would be awesome. I mean, what was interesting, though, if you looked at the point cloud from the previous slides, the point clouds are actually quite sparse. It's very difficult to get a lot of dense data out of that. Even when you're doing dense stereo reconstruction, you end up getting a lot of holes, to be honest. But eventually, we want to actually be able to provide a better geometry. If you look at existing Street View data, when you use the transitions in Click to Go, there's underlying geometry there that's sort of guiding that transition. So we'd like to be able to add that at some point.
So if I understand correctly, you have your own feature detector identifying these, and you are the images, panoramas seem really clean, really high quality, and they have some overlaps. Is it possible to then go back and look at these overlaps and train your classifier to figure out, identify better localization for features?
Definitely. We could do that. I mean, typically we sort of were trying to tackle our first order problems, which was getting something to work. So, I mean, just getting to the 95% was a huge victory, but yes, that would be an excellent way of improving our results, to get it to the 99.999%.
Yeah, this already looks very impressive.
Thank you, Okan.
All right, great. Well, we're bang on time, so let's thank the speaker again.